This is the second part of Core 3 Day 1, the derivatives of the inverse trig function. You just wrote down all the formulas after we derived the first two, and then you have formulas for the other four. Some practice with those would be a good idea, so that's where we'll start. Then we'll give you some to practice with, and you can come back to the video, pause it, try it, whatever speed you'd like in order to get yourself some good practice. So the first one they give us for practice together is the function is y equals arc sine of 2x plus 1. So some people do various things with this. Some people substitute in for that embedded function idea, they make a u function. You also realize then that whatever your embedded function is, the du, dx, or derivative of it also plays into the final derivative for that inverse sine function. So as I start to do that, I take the derivative of both sides, so dy dx, or y prime. We already have a formula for derivative of the inverse sine. 1 divided by the square root of 1 minus that u function squared. Then we need to multiply by the derivative of that u function, which is that du dx hanging out on the formula. As we do that, then we need to work on the cleaning up of some of these, and that's what's going to take some of you longer and more steps. So we're going to kind of work through and see where we can get some of that cleanup done. So in the numerator, we have a 2 factor. And in the denominator, we have some things to multiply out to see if we can find any places to make some factor canceling. So in the denominator, I have 1 minus everything that comes from the squaring of that u function. So I'd have to subtract a 4x squared, I'd have to subtract a 4x, and subtract a 1. The ones then in that radical sign are going to knock themselves out. They're going to zero out, so these two, leaving us with a denominator radical that has a factor of square root of 4 in it. So in the numerator, I have 2. In the denominator, I could factor out a square root of 4 factor, meaning 4 is a factor of both parts of this expression, leaving behind negative x squared minus x. That 2 in the numerator and the square root of 4 function will cancel each other out, leaving me with my final derivative in simplified form of 1 over the square root of the opposite of x squared minus x. It is okay to leave that radical in the denominator for this derivative. The next one's got an inverse secant function to it. Again, that same function, that u function 2x plus 1, just repeating that so that you can think about the fact of what u is and what u prime would be. So as you do that, to get the derivative for any arc secant or inverse secant, we'd be looking at 1 divided by the absolute value of the embedded function times the square root of the embedded function squared minus 1. So I'm going to be looking at quantity 2x plus 1 squared plus 1. Then I still need to multiply by du dx, or the derivative of that embedded function. The absolute value of 2x plus 1, I don't know its sign unless I know what x is. So I can't do much to that absolute value of 2x plus 1. I'm not sure if it's positive, I'm not sure if it's negative, so until then that would need to be evaluated with its absolute value sign to keep the correct value in there. But in that square root, I can definitely do some simplifying. So in that square root, once I square that quantity, we saw that in the last one, 4x squared plus 4x plus 1, and then there's a subtract 1 as part of our derivative, we see that we might be able to make some same simplifications as we did last time. So in the numerator, I have a factor of 2. The denominator, I've still got that absolute value of 2x plus 1 factor. I can definitely factor a square root of 4 factor out. So you can either write it as square root of 4 or write it right away as 2. The remaining factors inside would be x squared plus x. So the derivative for that function, we'll call it y prime. So the derivative for that equation would be 2 divided by absolute value of 2x plus 1. Take that back. The 2 cancels. I was in such a hurry to get a final answer that my 2's cancel. 1 divided by the absolute value of 2x plus 1. times the square root of x squared plus x. At this point, there's 2 for practice here for you. You can pause the video and then come back to it. I'll put up the answer to each one, and if you need to, then you can watch the part that gets you there. It might be a simplifying issue too that you need to check out. And then we'll do one application so that you've seen some like that. So pause the video right now. And you're back. So we'll do the derivatives for each one. First we'll give you what the derivative is, and then we'll show you where it came from. So derivative for this one, so that you can check a simplified form of it. Negative 6 divided by t times the square root t to the 4th minus 9. So we'll go through and actually work that one, but if you got it all simplified, then keep going to the next one and check it and skip that part of the video. So to do this first one, you might want to think about what that radical, or what that function could be rewritten as. So an equivalent function here would be inverse sine of 3t to the negative 2. So we might want to use that interchangeably. So when I go to take its derivative, again looking at one for inverse sine, I know that I need to do 1 divided by, and then the square root of, I'm going to be looking at 1 minus the u function squared. You can do it as 3t to the negative 2. I'm going to actually keep it as this. It just helps with simplifying later, squared. And then over here, what does help to keep it in that 3t to the negative 2 is to get the derivative, the du dx for that function, which is that. So that's the raw idea of what we need to do to carry out this derivative. To clean that up now, I want to be thinking about where each value belongs. So that negative 6 is a numerator value. That t cubed would be a denominator value, so we can get the negative power off of there. Then I want to see if under that radical sign, if I can get a common denominator for that. So what it is right now is it's 1 minus 9 over t to the 4th. I want to see if I can get a common denominator in there so I can pull a factor out. So negative 6 t cubed. Underneath the radical, then I would have t to the 4th minus 9 all over t to the 4th. That 1 over t to the 4th that I could pull out of the denominator under that radical sign, that's what I'm going to be simplifying with. So I have a t cubed. If I pulled out a square root of 1 over t to the 4th, in other words, that denominator t to the 4th, and I'll write it so you can see it, then I'd be left with the square root of t to the 4th minus 9. The square root of 1 over t to the 4th would be 1 over t squared. So I'd be looking at negative 6 t cubed times 1 over t squared times t to the 4th minus 9. And at that point then, we're looking at 6, 1t factor, and square root of t to the 4th minus 9. If it's a simplifying, then go back over it so that you're reworking that simplifying part and finding good factors and how to clean those up as much as possible. On the second one then, your final answer would be, so your derivative in terms of x, would be a negative 2 in the numerator. Again, a simplified set of this. A factor of x squared plus 1, and a square root of x squared plus 2. So that would be our final derivative. In this case, we can do something with the absolute value because of what they told us here. So I'll go through it now piece by piece, and if you need to stay with me, if not, move on for that final example. So y prime. Y prime is going to be, we need to walk this through cosecant inverse. Its derivative is negative 1, and then the absolute value of your embedded function times the square root of the embedded function squared, and then we've got a minus 1 in there. We also need to multiply by du dx, the derivative of the embedded function, which in our case is 2x. Here's what I know. If x is greater than 0, as they told me, no matter what, x squared is positive whether that's true or not, and when I add 1, then I still end up with a positive number. So because x is greater than 0, the absolute value of x squared plus 1 is definitely positive. That would be true even without x being greater than 0. X squared always results in a number 0 or bigger, and adding 1 would result in a positive outcome for that. So having the absolute value signs there will not change the value of that no matter what x is put in. So I can take them off. So in the numerator I have a negative 2x. In the denominator then I have a factor of x squared plus 1. And under the square root sign, again, trying to do any work to see if we can factor anything out. So underneath there we have x to the 4th plus 2x squared plus 1 minus 1. Again, that plus 1 minus 1 really zeroes out. So I'm looking at taking the negative 2x factor up here, the x squared plus 1. Underneath there then, I could definitely take out a factor of x squared. So if I do that, I'd be taking out a factor of x squared under the radical sign, leaving behind x squared plus 2 under the radical sign. The square root of x squared is x, so that x would cancel with that factor, and our final derivative would be, we'd have a negative 2 in the numerator, we'd have x squared plus 1 times the square root of x squared plus 2. All right, final one. An application, a particle moving along the x-axis so that the position at any time is given by that function x of t. This is a position time function. Find the velocity at the indicated value of t. So velocity is our first derivative. So if we're looking for that, we want to be thinking about x prime of t. It's an inverse trig function, so we know how to handle that. If you want to try to pause the video and come back to it after you've checked yours, go ahead. So we'll have 1 divided by square root of 1 minus our t over 4 squared. Then we need to multiply by the derivative of the t over 4. Might help you to think of t over 4 as being 1/4 t, so that you can see that its derivative is 1/4. So as I move through, I'm going to have a 4 in the denominator. And in this case, because you're about to use the derivative as an application, it wouldn't be as important to get this one cleaned up as much as you could, but it will make the calculation a lot easier. So if you needed to use this quite a bit more, I would definitely suggest it. And just for practice, let's do that right now. Many of you could use that simplifying practice. So in that radical sign, we need to see if we can come up with a common denominator, which would be 16ths. 16th is a perfect square, so therefore we can pull out a 1/16th square root factor. So I can take the 1, I already have a 4 in the denominator. If I pull out the square root of 1/16th, I'll be left behind the square root of 16 minus t squared. The square root of 1/16th is 1/4. So these two cancel out. My final derivative, much simpler than what we have, is that. So that's our velocity function, or derivative function. So then they're asking us, what's the velocity at a time of 3? So I want to evaluate my derivative at a time of 3. And that simplified form of it is going to make it much easier to do that. So 1 divided by 16 minus 3 squared. So we'd be looking at 1 divided by square root of 7, and just because we can, square root of 7 over 7 for our final velocity at 3 seconds. We don't have units, so we're not able to add the units per time. At this point then, start on homework. Tonight you have 4-3 day 1. Make sure you're doing some simplifying because that's a skill that needs some practice.